Hey everyone, and welcome to another explainer. Okay, today we are taking a massive leap forward. We're moving away from just writing basic line-by-line scripts, and we are stepping into the role of a true system architect. We're looking at Chapter 6, Logic, Routing, and Automation in Python. By the end of our time today, you're going to understand exactly how to build intelligent code that can actually make its own decisions.
Okay, let's dive into this. Take a look at these three primary structures: sequence, selection, and repetition. Basically, these are the fundamental building blocks of all computational logic. By default, Python just wants to execute statements one right after the other. That's the sequence on the left. But to build truly intelligent systems, we need to add selection, which gives our code branching paths based on logic, and repetition, which automates those iterative processes.
So here's our architectural journey for this explainer. We're going to move sequentially from the flow of control to directing logic and decisions. Then we'll power things up in the engine of automation, learn to pump the brakes with precision control, and finally bring it all together in mastering applied complexity. All right, let's jump right into section 1, the flow of control. So what does that actually mean when we're writing Python? Think of your code's execution kind of like a transit map. By default, a program runs sequentially, right? It travels down this straight, uninterrupted transit line from top to bottom. But as you know, real-world problems just aren't straight lines. We absolutely need rules to bend, route, and redirect this flow. We literally have to tell the execution precisely where to turn. And when it comes to setting up those specific routes, Python is famously strict about its blueprints. As the creator of Python, Guido van Rossum actually noted, making it part of the syntax guarantees that all code is properly indented. Python physically enforces spatial rules just to keep your architectural blueprint clean. Now, what's really interesting about this slide is exactly how Python enforces those rules. Unlike other programming languages that use those messy curly brackets to define blocks of code, Python just uses leading whitespace, literally just spaces or tabs. And it's strict. If your spacing is even slightly off, boom, the interpreter throws an immediate syntax error. It's an unforgiving rule, for sure, but honestly, it's brilliant because it forces everyone to write highly readable, beautifully structured code. Okay, moving on to section 2, directing logic and decisions. This is where our code actually wakes up and starts making its own choices through selection. The most fundamental decision-making tool we have is the if statement. If you trace the true and false paths here, you'll see the if statement evaluates a condition, in this particular case, asking if a user's age is greater than or equal to 18. If that evaluates to true, the flow diverts right into that indented block of code and prints eligible to vote. But if it's false, it just skips that block entirely. It's a simple, single conditional pathway. But you might be wondering, what if we need a backup plan? Well, that's exactly where the if-else statement comes in. This structure creates two mutually exclusive paths. Take a look at the logic checking which number is larger between num1 and num2 to find a positive difference. If the first condition is true, we take the left path. If it's false, the code safely diverts over to the alternative outcome block on the right. And remember, only one of these blocks will ever actually execute. So, what happens if our transit line hits multiple roadblocks and we have way more than just two possibilities? That's when we use the elif clause, which is just short for else if. Think of it like a traffic light. The program sequentially checks the conditions. Is the signal red? False. Is the signal orange? False. Is the signal green? True. The moment a condition evaluates to true, its specific block executes to print go, and then the entire structure terminates immediately. No further checks are made. And this brilliantly illustrates what happens when decisions get truly complicated, nested if statements. Python actually allows you to place an if-else structure entirely inside the block of another one. As you can see here, once we're inside one pathway, we can ask another, deeper question, like, say, making sure a denominator isn't 0 before we try dividing. You can nest these infinitely for highly granular, layered decision-making. It's almost like a giant logic puzzle. All right. Section 3, the engine of automation. Now that we have a solid handle on routing logic, it's time to mark the big shift from manual labor to true programming power. Think about this incredibly painful scenario for a second. If you wanted to print the numbers 1 through 100,000 on your screen, how would you actually do it? Would you sit there and manually type out print 1, print 2, all the way up to 100,000? Yeah, I certainly hope not. Notice the stark contrast between these two approaches. Over on the left, we have the brute force method, exhausting, wildly inefficient manual sequence writing. But on the right, the looping method. By utilizing repetition, we can just set a count to 1, define a condition to stop at 100,000, and let a tiny 3-line loop run the engine automatically. This automation is literally the beating heart of Python programming. So, the crucial point is knowing which loop to use. We use the for loop when we know the exact number of iterations in advance. It's designed for absolute predictability. If you want to traverse a predefined sequence, like the string Python right here, the for loop automatically fetches consecutive elements one by one. It prints p, then y, then t, and so on until the sequence is completely empty.
Now, the other main engine is the while loop. This one runs dynamically based on a condition rather than a set sequence. But it requires manual mechanics. First, initialization, setting a starting value. Second, the test condition, which is checked prior to every single execution. And third, the update step. And guys, I really want to caution you here. If you forget step 3, your control variable never changes, your exit condition is never met, and you will create a disastrous infinite loop that'll completely crash your program. Nobody wants that.
This diagnostic matrix makes it super easy to know when an architect should choose which engine. Use a for loop when you're traversing known sequences and you want the control variable handled automatically. Your risk of an infinite loop there is extremely low. On the flip side, choose the while loop when you're waiting for a specific dynamic state change. But remember, with a while loop, the iteration count is unknown. You absolutely must manually update your variables, and the risk of an infinite loop is high if you define it poorly. Moving on to Section 4, Precision Control and Overrides. So these iteration engines are incredibly powerful, but how do we actually rein them in so they don't run out of control? Well, sometimes you just need to abort a loop prematurely. That's exactly what the break statement does. Look at the bright red emergency exit on this diagram. If our loop encounters a condition where the variable num equals 8, the break command is triggered. It acts as a literal emergency exit. It immediately severs normal execution, entirely terminates the loop, and drops the program down to the very next line of code outside that block. Now, contrast that with the continue statement. While break destroys the whole loop, continue just bypasses a single cycle. In this example, if num equals 3, the continue command is triggered. It skips any remaining statements in the loop body for that single iteration and immediately jumps right back to the top of the loop header to evaluate the next cycle. So it's just a skip, not a total exit. All right, Section 5, Mastering Applied Complexity. We've got all our individual pieces now. Sequences, logic routing, loops, overrides. It's time to hook all these circuit boards, transit lines, and engines together. Let's move to and see how this builds into a real-world application. Check out this prime number generator. Look at how beautifully these simple structures layer together. We've got an outer for loop stepping through the numbers. Inside of that, an inner while loop checking for mathematical factors. Inside that, an if statement checking for remainders, and inside that, a break command acting as an intercept to stop checking if a factor is found. It's a highly efficient mathematical engine built entirely from those basic parts. And that brings us to the ultimate control board. This visual basically summarizes everything we've mapped out today. You start with a default line-by-line sequence. You add infinite architectural flexibility through nesting. You create dynamic branching with selection using if, elif, and else. You automate execution with repetition using for and while loops. And finally, you fine-tune the whole shebang with precision control overrides like break and continue. You now understand the core flow of control in Python. The pieces themselves are simple, but the systems you can build with them, they are infinitely complex. So now that you have the architectural blueprint in your hands, what complex system will you automate next? Get out there, open up Python, and start routing your own logic. Thanks so much for joining me on this explainer, and I'll catch you in the next one.